basic equations that we're going to graph from, and that's going to be standard form and vertex form. And I think vertex form will kind of look similar to what we did with the absolute values, but standard form might not look all that familiar with anything that we've done this year. So let me write these out for you guys here real quick. So standard form of a quadratic. Quadratic, I should mention, means the highest power of x is going to be an x squared. So if we have a quadratic function of any kind, it's got to have x squared as its highest power of the variable, and it has to have an x squared somewhere in it, otherwise it's not quadratic. So two different formats we're going to look at. You've got ax squared plus bx plus c. That's called standard form. We're going to actually do that, kind of more of a focus on that in a couple of days. The vertex form, this one I think will kind of look similar to an absolute value equation. You have a, and then in parentheses, x minus h squared, kind of like instead of an absolute value, I'm using parentheses that are squared, and then you'd have a plus k on the outside. Now, in these two formats, just so you know, the a in both of these is the same. So that number will be the same. Whatever it is, if we have the same equation written in both formats, the a value will be exactly the same. And then I'm just going to work on the vertex form just a little bit so you guys have this. But your h and k is going to be the vertex, like it's the vertex of an absolute value. So, sorry. Over here. Okay, so this HK is going to be the vertex of the parabola here. Whenever you have a quadratic, it creates a parabola. We're going to talk about that more today. But this works the same exact way as what the absolute value equations did, where whatever's inside with the x, that'll be the x coordinate of the vertex, and it's the opposite of what it looks like. And then whatever's outside that parentheses that are squared, that's going to be your y coordinate of the vertex. We're going to get into that a little bit more tomorrow, but just want to make sure you guys have both of these equations to start out. What we're going to do in actually the first example, and this is really the only algebra that we're going to do today, everything else is going to be graphing or describing something about a graph. We're going to convert these into standard form. So standard form is this one right above the ax squared plus bx plus c. It just means we got to get rid of the parentheses. So we're just going to multiply everything out, and then it's going to ask you to state the quadratic, the linear, and or the constant term. You might not have all three for these. You might just have two of them, but it depends on the question. You don't have to have all three of those, but we're going to state those once we get these in standard form. So, does anybody remember if you have, like I have y equals x plus 4 in parentheses, and then I have x minus 6 in parentheses, how would I multiply those together to get rid of the parentheses? Ethan, what do you think? FOIL. Okay, did anybody else do something different than FOIL? What'd you do? Yes, yes. Okay, I'll show you both, and you do whichever one you like better. That's what I want you to do. Okay, so FOIL, does anybody remember what FOIL actually stands for? Yeah? Yes. Okay. So basically you take the two first things, multiply them together, the two outer or outside some things, then the two inside or inner, and then the two last. If I do this, I just kind of think of it as a double distributive property. I need to multiply x by both of these guys in the second set of parentheses, and I need to multiply 4. Now, if you prefer a box, I'm just going to show you how to draw a little box. Basically, you have two terms in each of those little sets of parentheses. So you just draw yourself a little 2 by 2 box. And it totally doesn't matter, but put one of the expressions across the top and one of the expressions down the side. So I'm just going to put the x plus 4 across the top and the x minus 6 across the side. And the idea, if you like the box better, you basically find the area of each piece on the inside. So like x times x, you'd get, here, I'll just do it real quick on this one. So to get x squared, this would be like negative 6 times x, so negative 6x. Like a Punnett square from biology, if you guys have done that yet. 4 times x, this would be 4x. And then this corner, 4 times negative 6 would be negative 24. If you do the FOIL, you do the exact same thing. You get the exact same terms. It's just a little bit different format. So x times x still gives you x squared. X times negative 6 gives you negative 6x. 4 times x gives you 4x. And 4 times negative 6 gives you negative 24. So whichever one of those you like better. Some people like the box better because they're a little more visual. Some people like the FOIL better. Whatever your preference is, that's what I want you to use. The actual answer to the question, most of the time you can combine some like terms here. So here in the FOIL and in the box, the like terms are usually diagonal from each other. So just to combine those to write our final answer here, we'd have x squared minus 2x. So negative 6x and 4x would be negative 2, and then negative 24. So this would be that exact same quadratic in standard form. Okay, now there's a couple questions they're going to ask you to identify the quadratic, the linear, and the constant terms. So I'm just going to write Q for quadratic. Does anybody know what would the quadratic term be from that? Riley, what do you think? The x squared. All right, does anybody know what the linear term would be from that equation? Jonathan, what do you think? Exactly. And then if they ask for a constant, do you know, in general, what are you looking for if you're looking for a constant? Does anybody know what constant means for math? Yeah. It's just a number without a variable, yeah. So it stays the same. Constant is just a plain number. So the plain number there is negative 24. And that's all you have to do. And the reason it's called a constant, if it doesn't have a variable attached to it, if I would plug something in for a variable, that could change each of the other two terms. But if I just have a number, I'm not plugging anything in, so it stays constant. It doesn't change. So any plain number is called a constant. Linear, the key to that is linear is going to be the term with the x, and quadratic is going to be the term that has the x squared. Linear, if you think of a line, the highest power of x in a line, it would just be x. If you have a quadratic, the highest power of x is an x squared, so that's how you can find those terms. Okay, now I want to try another one with you here very quickly. The reason I put this on here is a lot of people will kind of mess up the algebra if it's in this format. This is actually an example of the vertex form. So let me just start out here real quick. And what does it mean if I square something? So if I have that x plus 3 squared, like, do you distribute the squared, or like how do you handle the x plus 3 squared? Does anybody remember? What do you think? Yes. Okay. So biggest thing people screw up on this, two biggest things. They would distribute the 2. Don't do that. The other biggest thing is they distribute the exponent. Don't do that either. So I'm just going to write the 2. If you square something, you are multiplying it by itself. So x plus 3 squared means you want to write that x plus 3 twice. Otherwise, you completely, if you distribute the exponent, you get it wrong because you completely miss out on the middle term. Anytime you square something, you're multiplying it by itself. And then I had that minus 7. Now, this is completely up to you. This is just my recommendation. Once you write that x plus 3 twice, once you do that, what I usually do is I do a FOIL or box just focused on that little set of parentheses, just like we did in the last question. And we're eventually going to multiply that by 2, but that's usually the easiest thing to tell people to work through that. Just keep that 2 out in front and just do a little FOIL, or if you like the box, please draw yourself a box. You're more than welcome. We'll get the same terms. X times x will give you x squared. X times 3 will give you 3x. Then you get another 3 times x, so you get another 3x. And 3 times 3 is not 6, which I put last period. It is 9, so don't mess that up like I did. And then I'm just bringing down the negative 7. If you want to do this in fewer steps than I'm doing, that's completely fine. I'm just trying to show you where it comes from. I'm going to combine my like terms real quick. The 3x and 3x will add up to 6x there in the middle. And I just want to do that before I try to distribute the 2. Once you do that, just the 2 only gets distributed to what's inside those little set of parentheses. And then at the very end, I'm going to subtract that negative 7. So we get 2x squared plus, let's see, 12x plus 18. Don't distribute the 2 to the negative 7 because that was not being multiplied by that. But at the very end, you can actually combine that with the 18. So I get 2x squared plus 12x, 18 minus 7 is 11. And so there's that same quadratic. We started with vertex form, and we actually put it into standard form, just multiplying it out. Usually requires some kind of a foil or box, whichever one of those you like better. All right, so if I asked you, just raise your hand and tell me, for that example, what would you tell me the quadratic term is? What do you think? 2x squared. It has to be the whole thing. Take the coefficient, the entire term. What would my linear term there be? 12x. And your constant, what's my plain number? 11, right? And that's it. So just identifying. Now, each one of those terms was positive. You don't notice I'm putting a plus sign in front of it. You could if you wanted. It's important on this last example, though, if it does have a negative in front of it or a subtraction sign, you want to take that with the entire term. So keep that in mind as you're doing it. These were all positive, so I didn't have a negative in front of any of them. Is anybody having a question? Okay, so just a little tiny bit of algebra, and that's pretty much all the algebra we're going to do today. The rest of this is about the graphs of a quadratic, which is the definition of a parabola. A parabola is just the graph of a quadratic. Does anybody know what the shape of a parabola is? Riley? Yes. Now, this is like an absolute value. Remember we had like the V, or we could have the upside down V. Parabola works the same way. It could be a right side up U shape, or it could be an upside down U shape. It depends on the equation, but in general, it's got a curve at the bottom there. It doesn't come to a point. The vertex depends on the graph. It is either the maximum or the minimum. I'm just going to write max or min point on the graph. Okay, so depends on how it turns. Now, this always messes people up a little bit because the maximum is actually where the vertex is at if it turns upside down. So it would look like that. It'll be the minimum point if the graph turns right side up. There's the vertex on the bottom. So the vertex is just either the very top or the very bottom of your U shape. It depends on which type you have, how it's turning. It can be max or minimum. It can't be both. And then the last thing we're going to talk about real quick, I'm just going to sketch a tiny little picture of a parabola. Axis of symmetry is a lovely vertical line, vertexal, if that helps you remember it, that goes right down the very middle of the parabola, and it splits it into two equal pieces. So that way, if we were to fold the parabola in half on that line, the two sides of the U, if I had drawn that perfectly, which I'm sure I didn't, would match up. Now, two quick things. First of all, this has to go through the vertex. This is the only point because the vertex will be right in the very middle. It has to go through the vertex, and it has to be a vertical line. So if it has to be a vertical line, it is x equals some number, and that's the equation. An axis of symmetry is an actual equation, so you'd have to write x equals a number. Now, the number will always be, that number is just the x coordinate of the vertex. So whatever the x coordinate of the vertex is, that will be x equals that number will be your axis of symmetry. So I'm going to have you guys just come over here real quick and look at this lovely parabola that's already graphed from you. And we're just going to talk about some different features, and then we're going to graph one by hand in a second. So can anybody tell me what point on this graph is the vertex? Hunter, what do you think? Yes, there's your vertex right there. Now, would you tell me, I know it doesn't ask this, but would you tell me on that graph, is that a maximum or minimum? Right, it's at the bottom, so this would be a minimum. So I know it doesn't ask you that. I'm just going to jot that down real quick. Now, the axis of symmetry is just going to be a perfect straight up and down, nice vertical line. It has to go through the vertex. So right there, I'm just going to sketch it in. So if we were to fold that parabola in half on that line, the two sides of the U shape would match up with each other. So it's just a vertical line, and it should just be the x coordinate of the vertex. So if you guys look through here, this went right through x equals 3, right? All these x coordinates are 3 as you go up and down. The y coordinates or sorry, the x coordinates are all the same. The y coordinates change as you go up and down, but all the x's are the same. So it has to be x equals 3. You don't want to just write 3 there, because then I'm like, okay, what does that mean? You're saying the line x equals 3 is going to split that parabola into 2 equal pieces. And then, we didn't really talk about this yet. This we said was a minimum, right? We said the vertex is a minimum. So I'm going to circle that real quick. But it says the minimum value. Does anybody know what the minimum value on that graph is? Or what that would be referring to? It's not a point. It's not like 3, 2 is the vertex. It's not that point. Does anybody know what the minimum value would be? What do you think, Hunter? 2. Yes. Okay. The minimum value, it's the y coordinate of the vertex. So it's just going to be 2. You don't have to write y equals 2 because that would describe a horizontal line, but the actual minimum value is 2. So all the x's, I know it goes up, right? But it does go gradually to the left and right forever. You would cover every single x value on that parabola. But in terms of the y values, there's no graph down here. So the lowest y value is 2 and everything else is above that. So that's why that's called the minimum value of the graph. It's going to actually be an x value. That's true for any graph. If it asks you for a minimum value, it's going to be the smallest y value. Or a maximum value would be the biggest y value if the graph turned the other direction. Now the last thing, this is actually a little geometry throwback. So there's 2 points on the graph. If you guys, they're really super tiny. There's a point that says P and a point that says Q. This says P and like a little, it should be a little 1, but I think I have like a, I don't know what symbol that is there. It's supposed to be P prime is what that's supposed to be. P prime and Q prime are what they call points that are corresponding to points P and Q. So you're not going to write the coordinates of point P and Q. What that little symbol means, it's a reflection over the axis of symmetry. So if you guys remember doing reflections in geometry, so point P is here. It's 2 spots away from the axis of symmetry. So the point that would fold up onto, if we reflected that over the axis of symmetry, is the point they call P prime. So that would be right here. So if they're asking for a prime, they're asking for the reflection of that point over the axis of symmetry. And let's see, this looks like 5, 6 is the actual point. So don't tell me point P. You want to tell me the point that it's reflection over the axis of symmetry. Same thing with Q. If you find Q up here, reflect that over the axis of symmetry. So it's 3 spots away. So you just go 3 spots away on the other side. And in that case, that's going to be your Q prime. So looks like 0, 11 there. Is anybody having a question about any of the descriptions we just did for the graph? Okay. Now, I'm going to have you graph by hand. This is the most basic version. We call this a parent function. It's just the most basic version of a lovely quadratic, which is just y equals x squared. There's no shifting, there's no like stretching, shrinking, nothing. This is just the most basic version, just y equals x squared, no other numbers there. So let me have you guys fill in this table over here. If I plug in the x value of -4, what do I get if I square -4? And I want to show you this just real quick, because if you just type like -4 squared on your calculator, it'll tell you -16, but is that correct? No, okay, and this is weird. So this is a little thing with the calculator. What the calculator reads that as, it thinks you're trying to do 4 squared and multiply that by -1. So if you ever want to square a negative number, it's just better to put that negative number in parentheses and then put the squared on the outside, because it doesn't read it the way you're intending it if you just type -4 and then square it. You want to square -4, so you have to put parentheses around that. So these guys should all be positive. Anytime you square something, it should make it positive. So if I square -3, positive 9. If I square -2, we get 4. If I square -1, we get 1. 0 squared is just going to stay 0. And then what you'll notice positive 1 and negative 1, the x-coordinates, they will have the same y-coordinate. So if I square 1, I get the same thing as if I square negative 1. If I square 2 or negative 2, both of them are 4. If we square 3, we get 9. Square negative 3, we get 9. This creates that mirror image, and your little axis of symmetry would be the y-axis here. So I'm going to have you guys graph these points on the graph. So the 16 is really close to the top. The vertex here is going to be 0, 0. And we're just going to go through and plot these points. And then I'm going to show you how to use this parent function to kind of cheat so we don't have to make a table for all these graphs. So don't turn the page just quite yet. We're gonna use this graph, and I'm gonna show you how to use this little graph so we can kind of cheat. All right, when you kind of go through and connect those, just do your best. Don't make it come to a point, like trying to make the best you can that it would kind of curve there at the bottom to make that U shape. And I'm just gonna jot down here that vertex is 0, 0. The axis of symmetry here would actually be the y-axis would go directly down the middle, so the axis of symmetry would just be x equals 0. Remember, any vertical line, vertexal, it's all the x-coordinates are 0. It is actually the y-axis. That's your axis of symmetry, though. Can anybody tell me what the domain would be? Like, how do I cover the graph left and right? What are my possible x values? Ethan, what do you think? Exactly. It looks like it goes up really fast, but this side does go left forever, this goes right forever, so you'd spread out to cross the entire x-axis. And that would be true for any parabola. Just like any absolute value, any parabola, that should be the domain. Hunter, go ahead. Oh, there. Yeah, go ahead. Yes, perfect. All right, now the range. You don't have any graph down here, right? When you do the range, go from the bottom to the top. The first y value you touch is on the vertex, that y-coordinate 0. That's exactly why he said to use a bracket, and then everything else goes up forever. Now, before you flip the page, okay, I'm going to show you this and see if you notice what I'm going to point out to you, and I'm going to ask you a question about it. I'm just going to use one side of the graph, and I'm just going to make it just a teeny tiny bit bigger on my screen up here so I can show this to you. Okay, now this works on both sides, but for the moment I'm just going to work on one side. I'm going to go from the vertex, and I'm just going to make like a little triangle between that and the next point. So I'm going over 1 and up 1. Okay, and then I'm just going to repeat that, and I'm just going to write down what I'm doing. So from that point I just was at, I'm going over 1 again, and then this time I go up 3. All right, and then from that point I go over 1, and I did a really bad job drawing that. I go up 5. And then from there I go over 1, and I go up. This goes from 9 up to 16, so that would be 7. Does anybody notice any kind of a pattern? Okay, so what would you tell me the sequence was? You add 2. So what would the next number be? 9. Exactly. Do you guys see this? And if I wrote these perfect, let me write these perfect squares. So if I do like 0, 1, 4, 9, 16. I know we didn't keep going up. I'm just going to write a couple more. Like the 5 squared would be 25, and 6 squared would be 36. Between these is 1. Between these is 3. Between these is 5. And it just keeps going, and it follows this pattern. Between this would be 9. Between these two would be 11. And that pattern would always exist anytime you have the perfect squares, which you will have when you have a quadratic. Now, what I usually do with people, just to help you use this to graph a little bit faster, usually the graphs are not tall enough to continue that pattern to keep, like on this one I went like 1, 3, 5, 7, and then it was kind of at the top, and this is a pretty tall graph. So I usually just tell people, I just use the odd numbers. I just start out with 1, 3, 5, and that's plenty to graph any quadratic that you have. And I'm going to write down on the back kind of how I use that, but let me make this more normal size again so I can see it. Okay, so we're going to use that pattern. Instead of making that table, there's that relationship between the perfect squares. It's just odd numbers, like 1, 3, 5, 7, 9, 11. It would keep going if you wanted to keep listing the perfect squares. So that happens if your A value is 1. So that pattern, like I said, just 1, 3, 5. Now, the way it works, you start from the vertex, and then you go over 1 and up 1. Then you would go over 1, up 3, and then you would go over 1, up 5. Every time you do this, you always just go over right and left one spot. It's not really a slope because it changes. The slope would be consistent, but you can use this pattern. So you go over 1 and then up the pattern for the graph. Now, it'll change up. We'll talk about this in a second. What if it's negative? What if it's a different number? You can still use this pattern, though, and I promise it's so much faster than making a table, if you can remember this. But it's just every time just over 1 on either side of the vertex and then up the pattern. So I'm going to give you just a couple graphs. We're not going to shift anything left or right today. So these are quadratics that are just manipulated just a teeny tiny bit. And we're going to put these on the graph here. So I have x squared minus 4. What would the vertex be here if I, instead of just x squared, I have x squared minus 4? Like, where would the vertex change to from what we did on the front? Exactly. So 0, negative 4. All that negative 4 is going to do is shift that U shape that we drew on the last example, just shifts it down 4. Okay, so let me plot this point. Okay, now, instead of sitting there and making a table, the A value here is 1, so I'm just going to use my 1, 3, 5. So from the vertex, all you're going to do is you're going to go over 1 on either side and then up 1. And that'll give you 2 more points. So on either side of that vertex, just go over 1, up 1 on either side. Now, from the 2 points you just stopped at, you're going to go over 1 and then up 3. That'll give you 2 more points. So over 1 and then up 1, 2, 3. On either side, over 1, up 1, 2, 3. And then once you're there from those 2 points you just stopped at, one more time, go over 1, and then this time we'll go up 5, and you'll see this will create that quadratic. Put you up, let's see, right up here. Just on either side, over 1, up 5. And you just go from the point you just stopped at to get to the next. And I'm just going to try my best to kind of make a U shape there. And that's all we got. Way faster than making a table. What do we think about the graph next to this? What would the vertex be? I have negative x squared plus 5. What do you think? Yes, ma'am. 0, 5. All right, now, how is the negative in front of the x squared going to change anything? Like the one we just did was x squared minus 4. Now I've got negative x squared plus 5. Exactly. Okay, now if you're, like the A value here is technically negative 1. If you want to think about that A value, multiply that by the little pattern, that will give you the pattern for this graph, which would just be negative 1, negative 3, negative 5. All it means is if it's negative, we're just going to go down. So this one, I'm going to go still over 1, but I'll go down 1 to get the next set of points. So there's my vertex, just on either side, over 1, down 1. Then from those 2 points, go over 1, and then we're just going to go down 3. That negative just flips the parabola to go upside down. And then to get one more set of points, I'm going to go over 1, and then down 5 on either side. And again, just do your best. Don't make it like pointed. Just do your best to make it a U shape. Does anybody have a question? It's not terrible. Okay, now, 2 things. I'm going to tell you the difference between what the A value is, but to tell you in general how to use the A value. If you have something in front of your x squared, it's not affected anything else. The If you have other values, the constant term does not affect this. It's totally just the a value, whatever's in front of the x squared. You take that and multiply that, just like thinking like a little distributive property, and that will give you the pattern for the graph if that just starts with something other than an x squared or negative x squared. So just take your a value, whatever's in front of the x squared, multiply that by your pattern. That'll give you the pattern for your graph. Now, this says ignore whether that a value is positive or negative, because that just tells you whether the graph goes right side up or upside down. But ignoring the negative, if that value is bigger than 1, we call this a vertical stretch. And what that should do to the graph is it should just make it more narrow than what we were just graphing, like it pulls it up. This is the same for absolute value graphs. And again, ignore the negative. If that a value is like a half or 2/3, something between 0 and 1, this is called a vertical shrink. And what that will do is that will actually make the graph like much wider U shape. And we're just going to practice these here real quick. So at the bottom, I have 3 graphs. And it just depends on the question, but the majority of these will say you need to plot at least 5 points. So what that would mean is if I did my vertex and I did at least 2 steps in my pattern, I'd have 5 points. A lot of the graphs we just did, we had 7 points, but we're going to try and plot at least 5 points so we can get a good idea of the graph. So we're going to try this one, and this one is y equals 3x squared. So does anybody know what the vertex would be if I have 3x squared? Ethan, we think? Yes, 0, 0. We're not shifting left, right, up, down. This would just start at the origin. Okay, I'm kind of far to the bottom. Now, here's what you do. Your a value is 3. So that's going to change how those perfect squares would be in terms of the pattern there. So I'm just going to multiply that real quick. The new pattern for this graph would be 3, 9, 15. You're not going to get there's no way that graph is falling up on the screen there to get the 15, but we should be able to at least get the first 2 steps. Alright, so all I'm going to do, start at the vertex, which is 0, 0, and from here, I'm just going to go over 1, but I'm going to go up 3, and that'll give us our stretch. So over 1, up 3, and you can fit just every time over 1, and then I'm going to go up 9. The 15 is going to be too tall for the graph, but we can get the 9 on here. So I'm going from 3, so to go up 9, we should be at 12. And you can see this is much more narrow than the parabolas we've been graphing. So that's a vertical stretch. Can anybody tell me what the vertex would be for the graph in the middle if I've got y equals negative 2x squared plus 7? What would the vertex be? The negative 2 affects the stretch and shrink. It's 0, 7. All of these will have an x coordinate of 0. If you have a plus or minus to the side, that'll just be the y coordinate of the vertex. So 0, 7. Now, my a value is negative 2. So you're just going to take and multiply that by your little pattern real quick. So the pattern here would be negative 2, negative 6, negative 10. And again, we might be able to get all 3. I don't think we're going to fit them on here. But from that vertex, it's always just over 1, and then I'm going to go down 2. And then I'm going to go over 1 and down 6. And I don't think I'm going to be able to do the over 1 down 10, but we'll see. So just from the vertex on either side, over 1, go down 2. You always just go over 1. Over 1, and then I'm going to go down 6. And down 10 is going to put me off the graph that I have here. So I'm just going to go ahead. I've got 5 points, so we're good. Just going to kind of connect that up with a curve. Now, on the very last one, I have to ask you to do me a favor because these are a little bit tricky. So your a value here is a half. This is going to be a vertical stretch, so this is going to, or shrink. This is going to be a little bit wider than the U-shapes that we've been doing. All right, now, my vertex, we're not shifting left or right, 0, and then I have this 1/2 x squared minus 4, so that's going to put that down 4 units from the origin, so just 0, negative 4 is going to be my vertex. Okay, now, Just promise me here. Because people will try to kind of think slope like rise over run, and you don't want to think that here. So I don't want you to use a fraction. Okay, I want you to use a decimal. So I'm going to say my A value is 1/2, and I'm going to write it as 0.5. And I'm going to write these as decimals because I don't want you to think like rise over run, okay? So 1/2, if I multiply that by 1, I just get 1/2. 1/2 times 3 is 1.5. And 1/2 times 5 is 2.5. So this is going to be my pattern. Okay, now, if it's 1/2, we're just going to estimate. It's not going to be perfect, and that's okay. So every time here, do not change this. From that vertex, you're going to go over one spot, and then I'm going to go up 1/2. So just like over one, and then just kind of do your best to go halfway in between the two little grid marks there. And then you're going to go, again, over one, up 1.5, which will put you on a nice point. So I'm on this halfway mark. I go over 1, I go up 1.5, and that should put you right on a corner. It should be on the point to -2. If you're on the other side, same thing. Over 1, I'm on the halfway mark. Up 1.5 would put you on the point -2, -2. And then this one will fit on here if you want to do one more step. Over 1, up 2.5. This won't be on a nice point, but you can kind of estimate. Over 1, up 1, 2.5. It would just be like at the halfway mark between 0 and 1 above the x-axis. So over 1, up 1, 2.5. And you guys can see, hopefully this one's a little bit wider than the other graphs that we've been doing here. Is anybody having a question? Okay, I'm going to stop.